Hello everyone in the week 2. So, in week 2 we are going to discuss about sorting and searching algorithms. But before that, this is the roadmap for today. That is algorithmic analysis which we did in the past last week. Then introduction to sorting. Then what basic sorting algorithms we are going to discuss. Then introduction to searching. Then which searching algorithms we are going to discuss and their summary and comparison. So if we go for the recap that what we did in the last week, so we discussed about the efficiency of the algorithms, like the worst case complexity, best case complexity, and the average case complexity. So bigger notation we use for the worst case complexity, which is the upper bound. Omega we use for the omega notation, we use for the lower bound, which describes your best case scenario. And the average of these upper bound and lower bound, which is defined by the theta notation, that is a tight bound which defines your both upper bound as well as lower bound. And this is also known as the average case complexity. Then let's move on to the sorting. So sorting, what we mean by the sorting? Sorting is arranging the elements either in an increasing order or non-increasing order based on a certain properties. Like if we are given some random numbers, we will organize them in the sequence. If we have to arrange them in the sequence of increasing order, so the smallest number will come first, then bigger than that, then bigger than, and so on. And the largest number will go at the end, right? If we have to sort the names, then we sort based, sometimes we sort based on the first name, sometimes we sort based on the last name, and so on. In that case, uppercase letters come first, then lowercase letters comes. So this is the sorting, that is arranging your elements in some definite sequence, whether increasing or non-increasing, which we call as decreasing. Why we require sorting? First of all, sorting is to organize your data in a certain way. Then we use the certain algorithms require sorted data. Like if a binary search, the binary search is all only the binary search is only possible on the data which is sorted, right? So, and if you have to represent the, like for example, in your class, if you have to represent the grades, then grades should be in the sorted order. If you have to represent the total, we use them in sorted order. So it is a way of representation, and number of algorithms require the input in the sorted form. So first of all, we will see here, we will discuss the some basic sorting algorithms which has a complexity of big of n square, right? And then we will move towards the advanced one like merge sort in the next week. So the bubble sort algorithms, basically these bubble sort algorithms belongs with the brute force family. So these algorithms are intuitive and easy to implement, and these are not efficient for large data sets. We can use them for the small data set, but we cannot use them. These are not efficient. It takes a lot of time to sort the large values. So the algorithms which we are going to cover are bubble sort, selection sort, and insertion sort. So the first one is the bubble sort. The basic idea is of bubble sort. We need to bubble up the elements. Like we compare the adjacent elements, and if the adjacent elements are not in the correct order, swap them. So, and we perform the process till all the elements are sorted, right? So, right. So this is the procedure or the function which we use for, this is just a pseudocode. It is not in any of the particular language. So we are using the bubble sort algorithm here. We are using the bubble sort algorithm here, and the A is the list of sortable items. Okay, let me, before the algorithm, let me discuss that how does it work. Let's say we are having the array 52819. So First of all, in the first pass, in the pass 1, we will compare element 5 and 2. These are not in correct order, so we will swap them. So after comparison, your result will be 25819. Then we are going to compare 5 and 8, that is the next two adjacent elements. These are in correct order, so no swapping will take place here. Then after that, we will compare next two elements, which are 8 and 1. So again, these are not in correct order, so swapping will be there and the element will become 25189. Then we will compare 8 and 9. Elements are in correct order, so we will leave them as it is. So after pass 1, your array becomes 25189. Make sure after every pass, the largest element goes to its proper position. Like if you see in this one, the element 9 is at its correct position, right? Then second pass, again we are going to start from the beginning. So we are going to compare elements 2 and 5. Now which is the second largest element? So it should be on its correct position now after the second pass. So 2, 5 we are going to compare. The elements are in correct order, so no swapping. Then 5 and 1 will be compared, not in correct order, so swapping will take place, so it will become 1, 5. Then we are going to compare 5 and 8, next two elements, correct order. Then we are going to compare 8 and 9, correct order, right? So now 8 and 9 are after the pass 2. The two largest elements are at their correct position. Then at pass third, the third largest element should be at its correct position. So again compare 2 and 1, not in correct position, swap it. Then compare 2 and 5, not in correct position, sorry, incorrect position, so no swapping will take place. And 8 and 9 and already are at position, so we do not need to compare with them. So your array becomes 12589. Then we do pass 4. We are going to compare elements 1 and 2. They are in correct order, so no swapping is required. So your array becomes 12589, which is the finally sorted order. So how many pass it took total? 4 pass. That means if their number of elements are n, then total passes are n minus 1. And how many total comparisons it took? It took 10 comparisons. Array is now sorted, right? And we stopped the algorithm early because when no swapping is taking place, that means the array is sorted and we stop it. This is called as optimized sorting algorithm. Okay, if we go for the code, so n is the length of the array. Then for I from 0 to n minus 1, we are starting from the first element till the last element. Then from I from 0, j from 0 to n minus I minus 2. Every time we are doing it minus 2. The reason is if in this array, after the first pass, this element is sorted. So in the next pass, we do not need to compare this element. So we will remove it. Then after the next pass, this element is at its correct position. So we do not need to compare it. So every time I'm going to subtract that one. If the elements are not in correct order, swap them. So that is the simple loop, right? Simple algorithm for the bubble sort. Time complexity is big O of n square. The worst case and average case time complexity is big O of n square. If you see here, there are two for loops and both are dependent on the value of n, right? So they both are going to n squared. Best case complexity is big O of n, which means the elements are already sorted. So one outer loop will execute only. Inner loop will not execute. So there will it will check for the swap, but nothing will happen. So after one loop, it will terminate. The space complexity is big O of 1 because bubble sort is a in-place sorting algorithm. That means it does not require any additional space for performing the sorting. So it does not take any extra amount of memory. Is it stable? Yes. If it is a stable algorithm because equal elements are not swapped here. And it is a in-place sorting algorithm, as I told you, because it does not require any additional memory for sorting like merge sort, which we will discuss next week. Then the next one is the selection sort. So the idea behind the selection sort is um, when we use the deck of cards, when we play any card game and we have a cards in our hand, what we do? Sometimes what we do, we take out the smallest card and put at the beginning. Then from the rest of the card, we again take the smallest card and put at the second position. Then again from the rest of the card, we take the smallest element and we put at the third position and so on. So that is the selection sort. What you need to do? Find out the minimum element. Basically, we in this one, we keep our array as two parts. One is the sorted and one is the unsorted. Yeah, we keep our array as sorted and unsorted. For example, your array is 5, 4, 1, 2, 3, let's say. The whole array is unsorted. So what you are gonna do, you will find the smallest element from this one. It is 1. So swap 1 with the first element of unsorted array. So it becomes 1, 4, 5, 2, 3. Now this is your sorted array. This is your unsorted. Now out of the unsorted array, again find out the smallest element, 2. So swap it with the first element of unsorted array. So it becomes 1, 2, 5, 4, 3. Now this is your sorted array, this is your unsorted array. Again from the unsorted array, find out the minimum element, smallest element, and swap it with the first element of unsorted array. So 3 will be swapped with 5. So it becomes 1, 2, 3, 4, 5. Now this one is your sorted array, this one is your unsorted array. Now again from the unsorted array, find out the smallest element, which is 4, and swap it with the first element of unsorted array. So 4 is swapped with 4. So your array becomes 1, 2, 3, 4, 5. This is your sorted array. This is your unsorted array. Now since there is only one element in the unsorted array, so we can stop the process. And now you can see the array is finally sorted. So this is the basic idea behind the selection sort. So again, in the procedure, in the pseudocode, what we are going to do, A is the list or the array of the elements which we want to solve. Now n equals to length of A, that is n is the length of array. For I equals to 0 to n minus 2, because as I said, we are not going to swap this element. When the first element is last element is left, we are not going to perform any operation, so the loop will go up to the n minus 2 elements. The minimum index, that is the index of the first element of unsorted array. For j equals to I plus 1 to n minus 1, if the element is less than, what you are going to do, you are putting the minimum index. But what you are doing here, basically, you are finding the smallest element, right? And once you find the smallest element, you are going to swap that with the first element of unsorted array. For example, the array is 64, 25, 12, 22, and 11. The whole is the unsorted portion. Now, if you find out the minimum one of this, it is 11. So 11 will be swapped with 64. So 11, minimum found at 11. So 11 will be swapped with 64. So after first pass, your array becomes 11, 25, 12, 22, 64. Where sorted portion is 11 and unsorted portion is this one. Now, in the second pass, we are just going to deal with the unsorted array. So this is your unsorted array. Again, find out the minimum element, which is 12. So 12 will be swapped with 25. So 12 will be swapped with 25. So this becomes your array, out of which 11 and 12 are the sorted portion and 25, 22, 64 are the unsorted portion. Then in pass 3, again we are going to do with the unsorted portion. You need to find out the minimum element of this. So 22 is the minimum. We are executing the algorithm of finding the minimum value in an array. Then 22 will be swapped with 25. So your array becomes this one. So after pass 3, the sorted portion is 11, 12, 22 and unsorted portion is 25, 64. Then again in pass 4, we are going to find out the smallest element of 25 and 64. So 25 is the smallest. So 25 will be swapped with 25 itself and you get the sorted portion is this and unsorted portion is this. And after the, since one element is remain in pass 5, so that is going to, nothing is going to happen over there. So that means it is automatically at its correct position. So your final sorting array is this one. So total passes here are 5 because n equals to 5 elements. Total comparisons are 10. First time 4 comparisons, then 3, then 2, then 1, then 0. Array is now sorted in an ascending order and it takes always big of n square comparison irrespective of order of elements. Whether elements are sorted or not, it always takes big of n square. The time complexity, so whether the best case, average case or worst case, all time complexities for this selection sort are big O of n square and the number of swaps is big O of n. Again, the space complexity is big O of 1 because it's an in-place sorting algorithm. It does not require any additional sorting, additional space. It is stable? No, because swapping can change the relative order of equal elements, right? Now, and it is in place, so yes, it is in place algorithm. Then let's go back, let's do with the insertion sort algorithm. Insertion sort algorithm is pick one card at a time and put it at its correct position. Insert it at its correct position. So again, it maintains two portions, sorted and unsorted. You take one element at a time from the unsorted portion and place it in the sorted portion at its correct position. And it requires shifting of elements because again it's a in-place sorting algorithm. It does not require any additional space, so it requires shifting of elements. For example, the array elements are 12, 11, 13, 5, 6. So in insertion sort, always remember that we assume that our first element at its correct position. So we always start with the second element. In insertion sort, we assume that our first element is at its correct position. So we start with the second element, right? So we start with the 11. 11. This is our sorted portion. This is our unsorted portion. So sorted portion, we take the first element of unsorted portion and fit it, insert it in the sorted portion correctly. So 11. 11 will be compared with 12. 11 is less than 12. So 11 should come before 12, right? So 11 will be swapped with 12. So your array becomes 11, 12, 13, 5, 6. And your sorted portion becomes 11, 12 and unsorted portion becomes 11, 5, 6. This one. The sorted portion is this, right? Then after pass 2, you need to come, the 11 is my current element, 13 is my current element. Now you will check the correct position of this in the sorted portion. So 11 is greater than 12, so it should come after 12. So 11 will be swapped, 13 will be swapped with 13, right? So your sorted array becomes 11, 12, 13 and unsorted becomes 5 and 6. Then your current element in pass 3, the current element is 5. So 5 will be compared with 13. It is less than 13. So compare 5 with 12. It is less than 12. So compare 5 with 16. 13. Sorry, 11. Compare 5 with 11. 5 is less than 11. That means 5 should come here. So we need to shift 13 over here, 12 over here, and 11 over here to make the space here for 5. We need to perform the shifting. Shift 13 at in place of 5, shift 12 in place of 13, and shift 11 in place of 12, so that you have a space here. And then copy this 5 element here. So your array becomes 5, 11, 12, 13, and 6. Now, after next pass, in the pass 4, your current state is 6. Now 6 is compared with 13. 6 is greater than 13. So 13 will be moved here, shifted here. Then 6 will be moved compared with 12. 6 is less than 12. So 12 will be shifted here. Then 6 is compared with 11. Since 6 is less than 11, so 11 will be moved here, that is shifted here. 6 will be compared with 5, but 6 is greater than 5. That means the correct position for 6 is here. So 6 will be copied at this place. And you, after the pass 4, you get the sorted array like this one, right? So finally sorted array is this. Total pass 4, total comparison 7, and insertion sort is good for the less number of elements, small arrays, right? Now let's take a look about the algorithm of this. So again, we are taking an array A. N is the length of array. We are taking a loop for I equals to 1. We are not starting the loop from 0. We are starting the loop from 1 because we assume that first element is sorted. Key is the element, the current element which we want to insert at its correct position. Now, you compare the element, you're finding the element at its correct position, and then we are shifting the element. This process is for the shifting. And once all the shifting is done, we put the key element at its correct position. So the time complexity of insertion sort is, again, for worst case and average case, it is big O of n square, but for best case, it is big O of n. Space complexity is again big O of 1 as it is in-place sorting algorithm. It is a stable sorting algorithm because the original order of elements are not changed. So if we compare the basic sorting algorithms with bubble sort, insertion sort, and selection sort, time complexity best scenario big O of n, big O of n squared, big O of n. Average is big O of n squared, n squared, n squared. Worst case n squared, n squared, n squared. Space complexity 1, 1, 1. Stable yes, no, yes. In place yes, yes, yes. Adaptive yes, no, yes. Method is bubble sort requires comparing and swapping adjacent elements, whereas selection sort requires selecting the minimum element from the array unsorted portion and swap it with the first element of the unsorted portion, whereas insertion sort requires inserting elements in the sorted position, in correct positions. So if we talk about the performance characteristics that when we use should algorithms, which one? So bubble sort, when to use? Just for educational purposes, we just to understand the concept of sorting, we use it, or for the small data sets, or with the data which is already almost sorted. It is an easy algorithm, easy to implement, easy to understand, and stable. Very slow for large data set, and it has many unnecessary swap which makes it complex. Selection sort algorithm, again used for small data sets, when simplicity is preferred because it is simple. Minimum swaps are big O of n. Again, simple implementation, it is not adaptive, not stable, and always big O of n square. Insertion sort algorithm, again for the small data sets because all these three has a complexity of big O of n square, right? So we can use these only for small data sets but not for large data sets. And efficient for small arrays, adaptive, stable, and online algorithm. Big of n square for reverse sorted data, and many shifts are for unsorted data. If you see the comparison for an array, bubble sort takes 4 passes, selection sort 4 passes. If the number of elements are 5, they all take 4 passes. Bubble sort requires 10 comparisons, selection sort requires 10 comparisons, insertion sort requires 7 comparisons. But swapping and shiftings, bubble sort requires 3 swaps, selection sort 3 swaps, and insertion sort 7 shifts, right? Now, after the sorting, let's go move on to the searching. Searching is in an array or in a list of elements, we want to find a specific element whether it exists or not. So, the element which we want to find is called as the search key. We call it simply key or search key, the value which we are looking for. If we got the element, if we find the element, if we find the key, then we call it as a hit. And if it is not available there we don't find it, it is called as a miss. So the algorithms which we are going to cover are linear search and binary search. Linear search is also called as sequential search. So linear search is, as its name suggests you, start from the first element and go till the end of the list by checking each element until the target element or key element is found or the list is ended. Like for example, if you are having a book and you want to find out a certain chapter, you go through every page of the book. You go through every page of the book to find out that chapter. So that is called as a linear search. The algorithm is, it's a simple algorithm. It takes two arguments. One is the list or array in which you want to find out the element, and one is the key, the element which you want to find out. This is the array and this is the element which you need to find out. So n is the length of the list. Now for I equals to 0 to n minus 1, that means we are going to search through the whole array. We are starting at index 0 going up to n minus 1. If ai equals to key, we are going to compare element at every index with the key, and if we find it anywhere, we return the index. And if the element is not found throughout the array, we return minus 1. Minus 1 always indicates element not found. So, the time complexity of linear search is, worst case is big O of n, because you are going to find out the whole array and still the element is not present or present at the end of the array. Best case is big O of 1. Let's say the element which you want to find out, that is the first element. So that is the best case. Average case is again big O of n. Space complexity big O of 1, as it does not require any additional memory space. There is no prerequisites to execute this algorithm. It works for any of the list. Then let's move on to the binary search algorithm. Binary search algorithm is based on the divide and conquer strategy. Divide and conquer strategy, divide your array every time and go for the array or the portion in which you are interested, in which you can find your element. Do not unnecessarily look for the whole array, right? So the first condition is, for the binary search, your array should be sorted. Binary search does not work on unsorted array. For example, if your array is, let's say, the elements contains are 1, 2, 4, 6, 8, 13, and so on, 15, right? How does it work? Let's say I want to find out the element 2, whether it exists in the array or not. What we are going to do? We will find out the middle element. Middle element is 6, right? Now, the key is 2. The element which I want to find, key, that is 2. So 2 is less than 6. That means since the array is sorted and 2 which I want to find out is less than the middle element. That means the element cannot be in the right half of the array. It can be only in the left half of the array. So we are going to search the element in the left half. So number of comparisons will be reduced. Again, take the middle element of this array, that is the 2. Now 2 is equal to the key element. That means element is found. So just in 2 comparisons, you find out the element, right? So every time your array size is reduced in half, every time your array size is reduced in half, and that is why the complexity of binary search is big O of log n base 2. So the algorithm is binary search can be implemented as an iterative algorithm, that is using just by the for loops, or it can be for loop or while loop using the loops, or it can be implemented as a recursive algorithm, right? We are using here the iterative version. Now, the condition, again the prerequisite for the binary search, the array must be sorted. It does not work on unsorted array. So what you require binary search, the parameters are A, the sorted list, and the key, the element which you want to find out. We maintain here low index and high index. So low is 0 initially, high is the last index of the array. While low is less than high, we are going to calculate the index of middle element. We are doing here integer division so that it prevents the overflow. If middle element, the element at middle index is equal to key, that means the element is found, so we return the index. If the element at the middle index is less than the key, which means the element is present in the right half of the array, so we are going to increase the index of low element. And otherwise the element is present in the left half of the array, so we will going to update the high index of the array, and we repeat the same process until the whole array is found or the element is find in the element. And if the whole while loop the element is not found, you return the -1. Just try to dry run the algorithm on a sorted array. So for example, the array is my sorted array is 2, 5, 8, 12, 16, 23, 31, 38, 45, 50, and we are looking for the element 31, right? And these are the array indexes because there are 10 elements in the array. So array indexes will be from 0 to 9. Now, so the low is 0, high is 9. We find out the middle index. Middle is 0 plus high minus low divided by 2, which comes out to be 4. So element at index 4 is 16. Now 31 is greater than 16. That means the element is going to be present in the right half of the array. So your low becomes the index 5 and high becomes the index 9. So low becomes mid plus 1. Low becomes index 5 and high becomes index 9. We are going, this is the middle element. We are, just a minute. Let me change the color. Yeah. So this is the low array, this is the high array, this is the high array, this is the middle element, and this is the low array. So we are going to discard the left half because my element is not present there. And we are just going to check the element in the right half. Then in second step, we again compare. Low is 5 now, high is 9. Again calculate the middle element which comes out to be 7. And A7 is 38. That means element at index 7 is 38. Now 31 is greater than 38? No. That means element is present in left half. So look, this is the array 38. Middle element is 38. 31 is less than 38. So we are going to find out the element in left half. It is not equal to middle. It is not present in the right half. So we are going to discard the right half here, and we will search the element in these two elements 23 and 31. Now again take the middle element. which comes out to be this one. Is 31 greater than 23? Yes, that means the element is present in right side. So element is present here. And then you compare it by itself. So yes, the low is 6, high is 6, the middle also comes as 6. So 31 is equal to 31, element is found, right? So you found out the element at index 6. So it takes very less comparisons. So if you see here, if I show you the overall summary, at step 1, the low is 0, high is 9, the mid comes out to be 9, 4. So the middle element is 16. Since 31 is greater than 16, so we go for the searching at the right side and we update the value of low. Then in second step, low becomes 5 as we updated the value of low here. High is still 9, middle comes out to be 7, element at middle index, that is at index 7, is 38. 31 is less than 38, that means the element is present in the left half. So we are going to update the value of high. So high becomes 6. Now low is still 5. So next step, low is 5, high is 6. Middle comes out to be 5. Element at index 5 is 23. Since 31 is greater than 23, that means element is present in the right half. So we are going to update the value of low. If element is present in the right half, update the value of low. If element is present in the left half, update the value of high. So element at low is equals to high, 6. Now the value of low is 6, the value of high is 6, middle comes out to be 6, which is at index 31. So 31 equals to 31. So element found at index 6. So this is how the binary search works. For all the cases of binary search, the complexity is big O of log n, because the search space is always divided into the two halves every time. It is in case of iterative algorithm, the space complexity is big of 1 as it does not require any additional space. But in case of recursive, as I told you, the binary search can be implemented as a recursive algorithm also. In case of recursion, the space complexity is big of log n as it requires additional memory space, additional stack space due to maintain the recursive calls. The prerequisite is sorted array. It requires a sorted array. So if we are going to compare linear search versus binary search, time complexity for best case, big O of 1, big O of 1, average, big O of n, big O of log n, time case complexity in the worst scenario, big O of n, big O of log n. Space complexity, big O of 1 and big O of n, big O of 1, big O of log n. Prerequisites none. Prerequisites array must be sorted. It is based on the sequential search, whereas it is based on the divide and conquer. Data structure which we use here, arrays or linked list, anyone, but it can use only arrays because linked list are sequential in nature and we cannot perform their divide and conquer. Basically, that is going to be that is not going to work because linked list are sequential and binary search requires random access to the elements. If we talk about the performance characteristics, the search method. Linear search is check each element sequentially, where binary search repeatedly divide the search space into halves. So number of comparisons, takes up to n comparisons, whereas binary search takes log n base 2 comparisons. Memory access pattern, linear search is sequential, whereas binary search is random. Cache performance, linear search is good for sequential access, whereas binary search is poor for random access. Implementation complexity, it is simple, but the binary search we can say it is moderate, not very complex, but not simple also. So it is moderate. Now, if you are thinking of that why binary search is big O of log n, look, binary search follows a divide and conquer approach, right? In which in which at every step we are dividing the search space into halves. So at step 1 there are n elements. At step 2 there are n by 2 elements because we discard the half of the array. Then at step 3 we take the half of the n by 2 which becomes n by 4. Then at step 2 n over 8 elements because the half of n over 4, and so on till when we will go till it will go up to kth step, and the how many elements will be there? N over 2 raised to the power k minus 1. If you see here, n over 2 raised to the power 0, n over 2 raised to the power 1, n over 2 raised to the power 2. If you find out a pattern here, n over 2 raised to the power 3. The first step 0, second step 1, third step 2, fourth step 2 raised to the power 3. So at kth step it will go over n over 2 raised to the power k minus 1 elements. And the algorithm stop when the n number of elements are just 1. When the search space is reduced to 1. That means n over 2 raised to the power k minus 1 should be equals to 1, right? That is the number of elements. So if we solve this equation mathematically, so n over 2 raised to the power k minus 1 equals to 1, which means n equals to 2 raised to the power k minus 1. If I take the logarithm log base 2 both sides, it becomes log n base 2 equals to k minus 1, or k equals to log n base 2 plus 1. Since 1 is a constant, we are going to drop it. So it becomes k equals to log n base 2. So the big O notation is log n. If we have n equals to 16, that is the 16 elements. So at first step, the indexes are 0 to 15. In the second, there will be 8 elements. In the third, there will be 4 elements. In the fourth step, there will be 2 elements. And in the fifth step, there will be 1 element. So how many steps? 5, right? And if you calculate log 16 base 2 plus 1, that comes out to be 5. If the value of n equals to 8, that means you need to take at most 3 to 4 comparisons to look for the element in the array. If there are 1200, 1024 elements in the array, the number of comparisons, maximum 10 to 11 comparisons are required. If there are 1 million elements in the array, then you require approximately 20 comparisons to find an element if it exists or not. So very drastic difference from the linear search and binary search. Look, if I'll say, if we compare it, if the array size is 10, linear search will require 10 comparisons, binary search will require 4 comparisons. 1000 elements, linear search will require same number of elements because the complexity is big O of n, while binary search will require 10 operations. 1 million, it will require the same number of operations, but binary search will require 20. For this much number of elements, this much number of operations, but binary search will require just 30 operations. So you can see the difference of operations, that how drastically the performance improves in case of binary search for large data set. So the sorting algorithm which we talk about, bubble sort, selection sort, insertion sort, so these all are having the big O of n square complexities. Whereas the searching, linear search and binary search, linear search works on big O of n, the complexity, and it is sequential in nature, it works on any of the list, whereas binary search takes big O of log n time, and it requires a sorted list. That is the prerequisite for this, that is must. If I say that why we are learning the big O of n square when we are having the better sorting algorithm like quick sort and merge sort, why we are learning these sorting algorithms with big O of n square. So basically these algorithms are the fundamental concepts, right? These are the basic sorting algorithms just to understand the algorithms, first of all. Second thing, if you are having a small data set, then these going algorithms are easier to implement instead of merge sort and quick sort. And binary search, as we said that binary search debugging, finding the first bad commit with git bisect. So basically we binary search is used everywhere actually in case of debugging, in database indexes, searching in large and sorted data sets, like you use in the phone books, dictionaries, everywhere. In a book, everywhere we use the concept of binary search to find out a element, right? So this was about this week. In the next week, we are going to talk about in detail that what is the divide and conquer strategy, and we will discuss about advanced sorting algorithm, that is the mod sort. It is really a very good algorithm and with the best, I will say, performance, big of n log n. And so this will basically you will understand that why what is the reason behind these efficient algorithms, right? And again, do not forget to perform your reading from the textbook and check out all the study materials, resources, complete your quiz, assignments, and take out your cornell notes. Do not um, forget and submit those on time, right? And if you have any question, you can email me, you can contact me, right? Okay, thank you so much. Bye, take care.